Hi there. This video is going to walk through 2 out of the 3 examples for deriving terms for a given electron configuration. So in this first video, we'll start off with our first case, which is a completely filled subshell. So what that means is that for each electron with a value of m sub s equal to plus 1/2, there's another with m sub s equal minus 1/2. So we have paired electrons. That also means that for each electron with a plus m sub l value, there's going to be another with a negative m sub l value. Okay, so let's take an example of an electron configuration given by 2p6. Okay, so that means that we would have a situation where we have 3 2p orbitals. Okay, remember we label these -1, 0, and +1 for our m sub l values, and then we can start putting in our electrons. So here, remember, we have a completely filled subshell, so we've got our 6 electrons, so if we just put those in our orbitals following our Aufbau principle, that building up principle, we end up with 2 electrons in each orbital. Now let's account for the m sub s and the m sub l for this particular electron configuration. Okay, so let's start with our m sub s. So big M sub s. So we're going to take the sum of all the little m sub s values for each electron in our electron configuration here. So in this case, we would see that each electron is paired. So for every plus 1/2, we get a minus 1/2. So we've got plus 1/2 and minus 1/2 in that first orbital, plus another spin up, plus another spin down in the second orbital, plus another spin up, plus another spin down in that third orbital. So here we've accounted for all of the spins of each electron in this particular arrangement, and when we add those all up, we get a value of 0. Okay, so if our big M sub s is equal to 0, that only leaves us with one option possible, that our big S, our total spin angular momentum quantum number, can be. Okay, so that value leads us to a big S of 0. We only get one option there. Okay, so we're going to do the same thing with the m sub l, big M sub l. So we're going to take the sum of all of the little m sub l values for each electron in our situation. So if we look here, we have 2 electrons with an m sub l -1, 2 electrons with an m sub l of 0, and 2 electrons with an m sub l of +1. Okay, so if we add those all up, we get -1 plus -1 plus 0 plus 0 plus 1 plus 1 turns out to be, once again, 0. Okay, so again, that's just a situation where for every value of m sub l, there's going to be a corresponding value of minus m sub l. So everything cancels out again. All right, so now we have a situation where the only possible value of big L, our total angular momentum quantum number, is going to be, once again, 0. Okay, so that maximum m sub l value essentially dictates what your big L can possibly be, and same for your m sub s. Okay, so that's why we're getting s equals 0 here, and L equals 0 for our possible options. So now if we put together our resulting term symbol for the situation, remember the term symbol represents a given combination of big L and big S. Okay, so those are essentially the values that we are looking for when we're identifying the term symbols. So we need a big L and a big S, which we just found. So that leaves us with a corresponding term symbol of, so if we look at our big L is 0, that means we have an S. Right? Remember the letter designations for each of those. So this S is different than our spin magnetic quantum number up here. Okay, so just be careful on those. So this S is the letter designation that comes from our L equals 0. That would be our SPDF options. Okay, so 0 corresponds to S. And then we want our multiplicity up in the corner. So we're going to do our 2S plus 1 is going to give us a singlet. Okay, so remember that 2S plus 1 in this case is going to give us a value of 1. That goes up in the corner as our multiplicity. Okay, so this is going to be our final term symbol for any case where you have a completely filled subshell. So you can go through and do this for any example that you want to practice where you've completely filled all of your subshells. So you could do one for d orbitals, s orbitals. Okay, it doesn't matter what situation you have. If you have completely filled subshells, you're going to end up with a singlet S term that describes those. Okay, so the next case we're going to look at is a situation where we have two electrons in different subshells, also known as non-equivalent electrons. In this case, we are going to have different values of either N or L, or both, depending on your situation. And then we also don't have to worry about our Pauli exclusion principle. Okay, so we don't have to worry about our electrons necessarily being paired in this situation. Okay, so the example we're going to look at for this situation is going to be a configuration of 1s2, 2s2, 2p, 3d. Okay, so we have a total of 6 electrons. So this would be an example of a carbon atom, an excited state of carbon. Okay, so the first thing that we're going to notice is that we have two completely filled subshells here. We're going to ignore those. Okay, so when you have an electron configuration that has valence electrons beyond closed subshells, you just are going to ignore the closed subshells. So that's where we already went through and determined that each of those would have a singlet S term associated with them. Okay, so here we're going to ignore those. We're going to focus on those outer unfilled subshells. Okay, so here we're going to focus on the 2p and 3d electrons. Okay, so in this case, we want to use our Clebsch-Gordan series approach to determining the total angular momentum, or big L, and total spin angular momentum, or big S. Okay, so here we're just going to identify the little l values for each electron. We'll start with the L. So here we will say that our L1, little L1, for that electron in the p orbital is going to equal 1. And then our little L2 for that second electron in the d orbital will be 2. Okay, so remember those values are coming from the type of orbital that your electron is in. Okay, so this 1 right here is coming from the fact that the numerical equivalent of a p orbital is L equals 1. This value here comes from the fact that we have a d orbital. Remember the numerical equivalent of L for a d orbital is 2. Okay, so now we just apply our Clebsch-Gordan series to our system. So our big L is going to be given by little L1 plus little L2, little L1 plus little L2 minus 1, and then you just keep going in that pattern until you hit the terminating value of little L1 minus little L2 absolute value. Okay, so in this case, we are going to first figure out where we're going to terminate so we don't keep going too far and wasting our time. All right, so our last value here is going to be the absolute value of 1 minus 2. All right, so we can go up to a value of plus 1. Okay, all right, so we'll stop when we hit 1. Okay, so little l1 plus little l2 is going to give us a value of 3. Little l1 plus little l2 minus 1, so we get 1 plus 2 minus 1, gives us a value of 2. L1 plus L2 minus 2 gives us a value of 1. Okay, and then we have hit our endpoint. Okay, so we can't keep going in our series because we've reached our terminating value of plus 1. All right, so then the options for big L in this case are going to be 3, 2, and 1. Okay, we can't go down to 0. Once again, remember we terminate here at plus 1. Okay, so we're going to do the same thing for our spin quantum numbers. Okay, so let's identify our possible values of little s for each electron in our system. Okay, so for that first electron in that 2p orbital, we know that our S1 is going to be plus 1/2, and then we have another electron that can also be spin plus 1/2. Okay, so now this part might be a little bit confusing to people. You might be asking yourselves, well, why are we doing all positive 1/2? Couldn't they be negative 1/2? And the answer to that is yes, absolutely. But the convention in doing this approach with the Clebsch-Gordan series is that if you have the option, you should give your electrons a spin plus 1/2. Okay, so you're only going to apply that minus 1/2 if you have to factor in the Pauli exclusion principle. Okay, so we don't have to do that here because we've got electrons in two different subshells, so they are both able to take on that plus 1/2 spin, that spin up configuration. Okay, so again, this is just convention for when we use this Clebsch-Gordan series approach. So just try to let go a little bit of any frustrations that arise from the fact that we're kind of just arbitrarily picking the plus 1/2 state here. Okay, so we're going to go through the same process we did with L. So we want our big S, so that's S1, little s1 plus little s2, little s1 plus little s2 minus 1, and then we keep going until we hit our terminal of the series. So let's figure out what our minimum value is going to be. So in that case, we're going to have absolute value of plus 1/2 minus plus 1/2. So we're going to end up with a value of 0 as our terminating value. So we'll start with our S1 plus S2. So in that case, we've got plus 1/2 equals 1. And then plus 1/2 minus 1 gets us to 0. And then we've hit our terminal value. Okay, so we can't go any further. So certainly not going to go into any negative values. Hopefully you can see that with either the L or the S. Okay, so these terminating points here basically guarantee that we get all positive, or I should say non-negative values. Okay, so now we have our possible options for big L and big S, and we're just going to put them together to create our different term symbol options for this particular electron configuration. Okay, so here we're going to have a few options for our term symbols. So we're going to have a few combinations of L and S. Okay, so we're just going to put them all together. So we're going to combine all of these different options. So the 3 and the 1, the 3 and the 0, the 2 and the 1, the 2 and the 0, the 1 and the 1, and the 1 and the 0. Okay, so we're going to end up with a total of 6 different terms for this case. So our L's, we want to get our letter designation for each one of those L's. So we have, for our L equals 3, that's going to be an F orbital. Okay, and then we're going to have 2 different multiplicities to go along with that based on our 2 different S values. So our S equals 1 is going to give us a triplet. So if we do 2S plus 1 there, that gives us a triplet. And then a 2S plus 1 here is going to give us a singlet. So remember, 3 is a triplet, and 1 we call a singlet. Okay, so each one of our L's is going to have a triplet and a singlet option that goes with it. So we'll have a singlet F and a triplet F. Okay, and then for L equals 2, that's our D letter. So we'll have a singlet D and a triplet D. And then for L equals 1, we have our P letter designation. So we get a singlet P and a triplet P. Okay, so there are the 6 options for possible term symbols for the 2P3D example. So again, this would be the approach you would use for any situation where you have 2 electrons in different subshells. Okay, so the key there is that we don't have to worry about our Pauli exclusion principle. We don't have to worry about pairing our electrons. So it makes life a little bit nicer there. Okay, so each one of these individual terms, we end up with 6 total here for our different combinations of L and S. Okay, each one of those terms would have a slightly different energy. Okay, so each term has a slightly different energy. So that will basically cause additional splitting in our spectra. Okay, so that gets us through our first 2 cases for deriving term symbols. I'm going to save the 3rd case for a separate video because that one is just a little bit more involved. So hopefully you found this part helpful, and we will continue on and take a look at our 3rd case.